Ever felt like you're just drowning in information, trying to get a handle on some really complex topic, but well, wishing there was just a clearer, maybe faster way to understand it all?
Yeah, that feeling is pretty common.
Well, you've found it. Welcome to the deep dive. We cut through the noise, basically deliver the essential stuff you need to become genuinely well-informed.
Hmm.
Today, we're taking a plunge into, well, the fascinating world, sometimes confusing world, of multi-threading and concurrency in iOS.
Oh, yeah. Definitely can be confusing.
We've gone deep into some foundational source material, specifically a core discussion from an iOS interview prep course. We've tried to pull out the absolute must-knows for you.
And our aim for this deep dive is, well, pretty simple. Extract the most impactful bits of knowledge from those sources. We're not just going to tell you what something is.
Right.
We want to explain the why behind the what.
Right.
Make sure you walk away with a comprehensive understanding, but without feeling totally overwhelmed.
Yeah, overload is the enemy here.
Exactly. The goal is to really elevate your knowledge, get you ready for those insightful discussions, whether it's, say, for a big interview or maybe just satisfying that intense curiosity you have.
Okay, so let's kick things off with something that might genuinely surprise you, especially if you're maybe earlier in your iOS journey. The role of data structures and algorithms, DSA, it actually shifts quite dramatically as you get more experience.
That's so true.
For freshers, the DSA bar is set incredibly high. Companies often judge almost entirely on it, right?
Absolutely right. But what's fascinating is how that changes. For experienced software engineers, the DSA difficulty level, it drops significantly.
Okay.
Yeah, companies aren't judging entirely on DSA anymore. They're using maybe basic to medium level questions, more like an initial filter.
Ah, like a first hurdle.
Exactly. So while our source material for this deep dive, it doesn't, waste time teaching how a linked list works from scratch or tree traversal.
The real basics.
Right, the super basics. It smartly focuses on equipping you to handle those foundational and intermediate DSA questions.
Yeah.
The ones that can act as your entry ticket.
That makes sense. That shift is key. But it brings us to maybe an even more fundamental question.
Okay.
Where did these concepts, concurrency, multi-threading, where did they even come from? What's the origin story behind it all? I mean, they didn't just pop up out of nowhere in iOS.
No, definitely not. You're hitting on the core truth there. It all starts way back with the operating system, the OS itself.
Like iOS, Windows?
Yeah, whether it's iOS, Windows, Linux, macOS, they all pretty much build on Unix fundamentals, deep down. The OS is the grand orchestrator, the decision maker. It's figuring out how to schedule all the tasks, how to use all the available resources efficiently, especially those CPU cores.
Okay, think about your iPhone, right? It's just one app really running at any single moment.
Almost never.
No. Your calling app, WhatsApp, YouTube, whatever app you're actually in, they all seem to be running, or at least appear to be running, kind of simultaneously, like a whole symphony of apps working together.
And that's where the really critical distinction comes in between concurrency and parallelism.
Okay, let's break that down.
Yeah, let's use that classic movie ticket queue analogy. It works pretty well.
Okay.
Imagine you're at the cinema. Concurrency is like having two queues, two lines of people, but only one ticket counter is open.
Ah, okay. So only one person gets served at a time.
Exactly. It looks like both lines are moving, maybe, because the cashier switches back and forth quickly, but only one person is actually buying a ticket at any single instant. The OS is that cashier, rapidly deciding which task gets attention for a split second.
Got it. So it looks parallel, but isn't really.
Right. Now, parallelism. That's when you have two queues and two counters open.
Ah, more resources.
Precisely. You genuinely have more resources, more CPU cores, which means truly simultaneous execution. Multiple tasks are literally running at the exact same moment in time.
Okay, that's much clearer. Two lines, two counters parallel, two lines, one counter concurrent.
You got it. And the OS achieves this magic, especially on a single core, through some pretty clever tricks, like context switching.
Context switching.
Yeah, it saves a task's entire state, its local variables, values in the CPU registers, everything it needs to remember where it was, saves that context, then switches to another task, runs it for a bit,
And then comes back.
and then can load back the first task's context and pick up exactly where it left off.
Mhm.
And there's also time slicing, where the OS just gives each task a tiny slice of time to run before switching.
Wow, that sounds complicated.
It is, deep down. Now, you probably won't have to, whiteboard these low-level OS things in an interview,
Okay, good.
but understanding they exist gives you a much deeper appreciation for the power that something like GCD is actually harnessing under the hood.
That's a fantastic breakdown. And speaking of harnessing power, in iOS, the main tool, the big fundamental concept for managing all these tasks, concurrent or parallel, is Grand Central Dispatch, GCD. This is where it gets really interesting for us as iOS devs, right?
Precisely. At its heart, GCD works with dispatch queues. And put simply, think of it like any normal queue. It follows the first in, first out rule, FIFO.
Okay, first come, first served.
For starting the task execution, yes. But, and this is a really crucial nuance, the order in which tasks finish. That can definitely vary. Depends on the queue type and how you actually dispatch the tasks onto it.
Okay, so they always start FIFO, but how they finish is where the difference lies. Let's dive into that, the core types. Serial queues versus concurrent queues. Maybe with some analogies.
Good idea. Analogies help. So a serial queue. Think of it like finishing your entire meal before you even think about getting back to coding.
Okay, total focus on one thing.
Exactly. One task has to complete entirely before the very next one in the queue even begins. The order of start and finish is perfectly maintained. Predictable.
Got it. One track mind. What about concurrent then?
A concurrent queue is more like maybe having a coffee break while you're still technically working.
Huh. Okay, multitasking.
Sort of. Tasks can interleave. They start in the order you added them, FIFO, yes, but the finishing order becomes unpredictable because the OS can switch between them, give resources to one, then another, based on what's available and how complex the tasks are.
Like brewing coffee while you quickly reply to an email.
Perfect analogy. They happen kind of at the same time, but maybe one finishes before the other unexpectedly.
Okay, serial is strict order. Concurrent allows interleaving. Makes sense.
Now, building on that, there's another common point of confusion, something that often trips people up.
Uh-oh. What is it?
The difference between synchronous, sync, and asynchronous, async. It's really vital to get this. These are behaviors. They describe how you add a task to a queue. They're not types of queues themselves.
Ah, okay. So you don't compare sync to serial.
Exactly. You shouldn't compare sync async directly to serial concurrent. They're different concepts. You can apply sync or async behavior to both serial and concurrent queues.
Right. So what's the difference in behavior then?
Sync. When you dispatch a task sync, imagine locking a door and standing there, waiting for someone inside to finish before you move on.
Okay, sounds blocking.
It is. Your current code execution literally stops, pauses, and waits for that dispatch task to complete. The compiler does not return immediately to run the next line of your code.
It just waits.
It waits until the sync task is totally done. This is why it blocks the current thread. And critically, why it can freeze your app or even crash it if you do this on the main thread.
Yikes. Okay, avoid sync on main thread. Got it. What about async?
Async is totally different. It's like handing off a task, maybe giving someone tea and saying, drink this whenever you like, while you immediately turn back to your own work.
Ah, fire and forget, kinda.
Pretty much. The task is given to the OS to handle on the target queue, but your current code. It continues executing immediately. The compiler returns right away to the next line.
So no waiting, no blocking.
No blocking. This is almost always what you want for smooth app performance. It keeps your app responsive, fluid. The user doesn't see freezes.
Okay, async sounds like the default choice most of the time then. But you said almost always. Are there any times where sync is actually the right call, even, dare I say it, potentially involving the main thread somehow? Or is that just always wrong?
That's a great question. Because you hear blocking the main thread and immediately think, never, ever do that.
Right.
But sync isn't inherently evil. It's crucial for certain things,
Yeah.
particularly around thread safety, when you have shared resources.
Shared resources, like data multiple threads might access.
Exactly. Imagine you have an array, maybe a counter,
Right.
that different parts of your app running on different concurrent queues might try to read from or write to at the same time.
That sounds like a recipe for disaster.
Race conditions?
Precisely. Data corruption, unpredictable state. So one common pattern is to create a dedicated private serial queue just for accessing that shared resource.
Okay, a private queue.
And then whenever any part of your code needs to read or write that shared data, you dispatch that read or write operation sync to that specific private serial queue. Ah, so the sync call blocks that private queue, ensuring only one operation happens at a time on the data.
Exactly. It acts like a mutex, a lock. It ensures sequential access to that specific piece of data, protecting its integrity.
But it doesn't necessarily block the thread that called sync for long, especially not the main thread if the work is quick.
Well, a calling thread does block until the sync task on the serial queue completes, but if the task is very fast, like updating a simple property, the block might be negligible. The key is you're not blocking the main thread with long-running work, and you're protecting your shared state. So sync has vital uses, just not usually for dispatching long tasks directly from the main thread.
That's a fantastic clarification. It's about using the right tool for the job safely. Okay, so for you, the listener, knowing all this, Apple gives us another tool, right, to kind of guide the OS quality of service, QoS?
Yep, quality of service, QoS. It's essentially your way, as the developer, to communicate the importance or urgency of a task to the OS.
So you're helping the OS prioritize.
You are. You're giving it hints so it can make better decisions about resource allocation, CPU time, energy efficiency, all for the best possible user experience.
Makes sense. So what are the main types?
There are 4 main QoS classes. At the very top, highest priority is user interactive.
User interactive. Sounds important.
It is. This is strictly for tasks that directly affect the UI and need to happen right now for the app to feel responsive. Think smooth scrolling, animations, handling touch events, drawing updates.
Okay, anything the user sees and interacts with immediately?
Pretty much. The OS is super concerned about UI performance. So if UI updates are involved, user inactive is the way to go. Below that is user initiated.
Still sounds user-focused.
It is.
Yeah.
Second highest priority. These are for tasks the user starts, and they want results quickly, but it's not necessarily updating the UI frame by frame. A great example is loading more data when you scroll down a social media feed like Instagram or LinkedIn.
Ah, you tap load more or scroll, and you expect it fast, but it's not an animation.
Exactly. You want the data reasonably quickly for a seamless experience, but it's not quite the same immediate demand as a UI animation. Then comes utility.
Utility, lower down.
Third priority. These are for longer running tasks, maybe tasks where the user sees some progress, but it doesn't directly block them from using the app. Think downloading a movie or a large file in the background.
Like in YouTube or Netflix, you see the progress bar.
Perfect example. The user knows it's happening, they're waiting for it, but they can still browse around and use the app while the download progresses. And finally, the lowest priority is background.
Background. Makes sense.
This is for tasks that run behind the scenes, often long-running. And the user isn't really aware of them or waiting for them. Things like database maintenance, indexing, or performing backups.
Like maybe a WhatsApp backup overnight.
Exactly like that. The user doesn't care if it finishes in 5 minutes or 30 minutes, as long as it gets done eventually without impacting their active use of the phone.
Okay, user interactive, user initiated, utility, background. Seems clear.
It seems clear, but here's a critical insight, a common pitfall I mentioned from the source material.
Oh.
Overusing the high priorities, especially user interactive. Developers sometimes think this is important to my app, so I'll mark it user interactive.
Right, make it go fast.
But if you mark too many things as high priority, you can actually starve other important system processes or even other lower priority but still needed tasks within your own app. It can paradoxically make the whole system, including your app, feel less responsive.
Ah, the everything is urgent problem again.
Exactly. The real skill is in accurately communicating the true nature and urgency of the task to the OS, not just trying to artificially boost everything.
That's such a vital point. Don't cry wolf with QoS. Okay, we've got GCD basics, queues, sync-to-sync behaviors, QoS, but sometimes tasks are more complex, right? Like interconnected. Does GCD help with orchestrating those?
Absolutely. There are more advanced tools. 2 incredibly important ones are Dispatch Work Item and Dispatch Group.
Dispatch work item, what's that for?
A Dispatch Work Item is super useful, especially because it gives you the ability to cancel tasks you've dispatched via GCD, which you can't easily do otherwise.
Cancel tasks? Why would I need that?
Think about a search bar. You start typing PRI.
Then you don't want an API call for P, then PR, then pre-RI.
Exactly. That's incredibly wasteful. With a Dispatch Work Item, you can implement something called debouncing. Each time the user types a character, you schedule a search task using a work item, but you also cancel any previous work item for that search.
Yeah.
You only let the search actually execute if there's been a brief pause in typing, say 300 milliseconds.
Ah, so it waits for the user to pause typing before searching? Clever.
Very useful. Another place is preventing multiple quick taps on a button, like a submit button in a banking app. You can use a work item to disable the button, perform the action, and only re-enable it via the work item when done, preventing accidental double submissions.
Nice. Okay, that's dispatch work item for cancellation and control. What about dispatch group?
Dispatch Group is all about coordination. It's designed for situations where you need to run multiple asynchronous tasks, potentially on different queues, and then do something only after all of them have finished.
Like waiting for several things to complete?
Precisely. The classic example is loading a complex screen or dashboard, maybe in an e-commerce app like Amazon or Flipkart.
Oh,
To show that main screen, you might need to make several independent API calls. One for product categories, one for special offers, maybe one for user location data.
right. They all run separately.
They can run concurrently, async. But you don't want to display the dashboard or maybe allow the user to proceed to the next screen until all of those API calls have successfully returned their data.
Because otherwise the screen would be incomplete or show errors.
Exactly. A dispatch group lets you enter the group for each task you start, leave the group when each task finishes, and then you can set up a notify block that only executes once the group count reaches 0, meaning all tasks are done.
It's like a gatekeeper ensuring everything is ready.
Perfectly put. It ensures all your ingredients are ready before you try to bake the cake. Very powerful for orchestrating complex workflows.
Okay, we've covered a lot conceptually, and you mentioned the source material had practical Xcode examples. Thinking about those, what were the key takeaways, like visually seeing the code run?
Yeah, seeing the code execute really solidifies these ideas. What stood out was serial queues are completely predictable. They consistently maintain execution order. If you dispatch task A, then task B to a serial queue, A always finishes before B starts. Like the 100-110 loop finished before the 300-310 loop in the examples.
Okay, serial is reliable order.
Absolutely. Also, it reinforced that normal sequential code, just lines of code one after another outside of any GCD dispatch block. That always executes serially too. Line 5 doesn't run until line 4 is done.
Obvious maybe, but important.
Crucial. That's why the 200-210 loop in the examples always finished entirely before any subsequent code outside an async block was even considered. But then the global concurrent queues using async, that's where you saw the apparent randomness. Truly unpredictable start and finish orders. Sometimes the 0-10 loop started, sometimes the 50-60 loop started first. Even if dispatched later, they interleaved. It perfectly demonstrated the OS dynamically scheduling tasks on available cores.
Shows the power and the unpredictability of concurrent async.
Exactly. You rely on the OS to manage it efficiently, but you don't control the exact micro-timing.
Okay. Now, for you listening, to really cement this and push your understanding further, here are a couple of thought-provoking challenges, straight from our source materials, kind of homework questions. Ready?
Let's hear them.
First, what stands out to you personally? In those source examples, sometimes the global queue tasks like the 0-10 and 50-60 loops actually started before the normal sequential loop, the 200-210 one, even though the dispatch call came later in the code. But other times, they waited until after 200-210 finished, and sometimes 0-10 ran before 50-60, sometimes the other way around. Why does this seemingly random behavior happen? What factors are at play there?
Good one. That gets you to think about OS scheduling.
And the second challenge, maybe a bit more fundamental, the question of thread versus queue. What is the fundamental difference? They sound related, but they're not the same. And crucially, when do you think about using one concept versus the other in your actual iOS development?
Ooh, yeah. Thread versus queue. That's a classic point of subtle distinction. Pondering these questions, maybe even trying to reproduce the code behaviors yourself in Xcode. That's how you move from just knowing the definitions to truly understanding the underlying system. It's about the OS behavior, not just memorizing API calls.
Wow. Okay, what an incredible amount of ground we've covered today. Seriously, deep dive. From the OS roots, concurrency versus parallelism.
Yeah, all the way through GCD, the different queues, sync versus async.
QoS, those are super useful dispatch work items and dispatch groups. You've just gained, hopefully, a really solid understanding, a shortcut to being well-informed and ready for those complex discussions or tricky interview questions.
Absolutely. And maybe one final thought for you to chew on as you continue exploring. Consider this. Your app has some really critical, high-priority UI animations running needs that user interactive QoS. But at the same time, maybe it's doing a large data sync in the background, marked as utility or background. How does the OS really balance these completely different demands, especially when the system load changes, maybe the battery's low or other apps are busy? How would you architect your task management using queues and QoS to ensure that user experience stays consistently smooth, no matter what else is happening on the device?
That's a great real-world scenario to ponder, how to keep things smooth under pressure. Thank you so much for joining us on this deep dive into iOS concurrency. We really hope you feel more confident, maybe more curious than ever. Keep learning, keep exploring those nuances.
Keep coding.
and we'll catch you on the next Deep Dive.